Hello everyone, this is the Superior Spartan Engineering team here to talk to you about the Shaw Lane Power Plant Rehabilitation Project. I'm Morgan Hutchins, the project engineer. Tommy Graff is our transportation engineer. Ben Gerton is our structural engineer. Jillian Pelzer is our pavements engineer. Hannah Watts is our hydrology engineer, and Tyler Conch is the environmental engineer. The project is located centrally on the campus of Michigan State University in East Lansing. More specifically, the project site is located at the intersection of Shaw Lane and Red Cedar Road, just southeast of Spartan Stadium. To accommodate the 2020 Vision Master Plan, the decommissioned Shaw Lane Power Plant will be reconstructed into an academic building, known as the Shaw Lane STEM Building. The rehabilitation is also intended to reconstruct the surrounding area to meet the current and future needs of the MSU community. The Superior Spartan Engineering team has developed a list of 3 major goals to help achieve the Vision 2020 Master Plan. Goal 1. Create a new building that is compatible with existing infrastructure and uses energy efficiently. Goal 2. Design roads as complete streets that prioritize pedestrians and include a bike system. Goal 3. Minimize the negative impacts of the Red Cedar River by protecting land and using green infrastructure. The red outline shows the scope of the project. The rehabilitation requires for the intersection of Shaw Lane and Red Cedar Road to be reconfigured to improve the overall experience of the roadway and promote safety while maximizing the movement of people and minimizing the movement of cars. Parking spaces will need to be reconfigured. There will also be minimal pavement improvements along Shaw Lane Road and Red Cedar Road. The Shaw Lane STEM building must meet all of Michigan State University's building requirements, which include ensuring there is a certain amount of space allocated to different sized classrooms and offices, as well as having an occupancy of 2,696 people. The hydrological system of this area must be redesigned to have a functioning stormwater management system. With the STEM building being in the floodplain of the Red Cedar River, it is especially important to have a design that can account for major flooding events. The new construction will increase the impervious area substantially, which increases runoff, so many low-impact designs will be implemented to decrease the amount and rate of runoff.
Hi, my name is Tommy Graff, and I'm a transportation engineer at Superior Spartan Engineering, and I had the pleasure of working on this project. I think it's best to start by going through the design objectives that pertain to transportation engineering. The redesign of the Red Cedar Road and Shaw Lane intersection to create a safer, more efficient, and more intuitive intersection, the closure of North Shaw Lane to vehicle traffic, and the implementation of a new bike path along North Shaw Lane that connects to the current bike path system, the conversion of South Shaw Lane to accommodate two-way traffic and to remediate any parking capacity if affected. The design decisions will take the MSU campus master plan into account, specifically to maximize the movement of pedestrians first, bicycles and non-motorized transportation second, and private vehicles last. The reclaiming of surface lots for green space, and to establish a coordinated bike system and designing complete streets, prioritizing safety and comfort. Here is an overhead view of the entire design to show how it fits into the surrounding environment. We will now go into detail about the different design aspects. To handle the traffic volumes of the current North Shaw Lane and South Shaw Lane, the new South Shaw Lane will be expanded from 2 lanes to 5 lanes to accommodate for the North Shaw Lane closure. South Shaw Lane will be expanded north into parking lots 39 and 40. Red Cedar Road will also be expanded from 3 lanes to 5 lanes north of the intersection and from 4 lanes to 5 lanes south of the intersection. Red Cedar Road will also have a northbound and southbound bike lane as it currently does. The design speed of Shaw Lane is 25 miles per hour. This is to remain consistent with the existing speed limit so drivers have a familiar driving environment. The designed vehicle is a city bus or a BUS 40 due to the CATA station's location on Shaw Lane and the extensive use of buses around campus. Each leg of the intersection has a left turn only lane, a through lane, and a through and right turn lane. In addition, Red Cedar Road will have a northbound and southbound bike lane. Using the Federal Highway Association, the corner radius was determined to be 21 feet. This is to keep the southeast corner unaffected by the new intersection design and to allow a safe turn by right-turning vehicles. A 21-foot radius allows for a safe and slow turn for passenger vehicles, while a city bus will be able to make a safe, slow turn with minor lane encroachment. Due to the 2 lanes in the direction of travel for a right turn, the minor lane encroachment will be acceptable. The lane width of 11 feet was chosen due to the low speed and nature of the roadway in a high pedestrian traffic area. The pedestrian crossings will have a width of 10 feet. Each leg of the intersection has a left turn lane with a permitted and protected signal phase. Using a 90-second cycle length due to the urban setting and high pedestrian movement, and the peak hour volume for each left turn lane, the left turn lane storage length could be determined. The maximum left turn volume at peak hour is 115 vehicles. A storage length of 100 feet allows for more than enough capacity at each leg of the intersection. The storage lengths west of the intersection on Shaw Lane were adjusted according to the geometry of the roadway to make for a safe adjustment into the left turn lane. The left turn lane south of the intersection on Red Cedar Road was adjusted to allow for a dual turn lane into the parking lot 56 and the left turn lane through the intersection. The traffic signal will have an actuated signal time in order to adapt to the high fluctuation in hourly traffic volumes throughout a 24-hour period. To promote the use of bicycle and pedestrian travel as part of the 2020 Campus Master Plan, sidewalks and a new bike path will be installed to connect to the existing system. A new bike path from the intersection of Red Cedar Road and Shaw Lane will cross through the new green space in a northeast direction towards Lot 50 and then continue east to Farm Lane. The bike path has a width of 11 feet with 1 lane in each direction of travel. The new green space is located in the remaining footprint of Lot 39 and North Shaw Lane directly north of Lot 39. The existing mixed-use path along the south side of Shaw Lane will connect to the new bike path by crossing Red Cedar Road and Shaw Lane. The existing bike lanes on the side of Red Cedar Road will be relocated to the outside of the new roadway with the lane expansion and continued all the way to the new intersection. The new bike lane along Red Cedar Road has a width of 5 feet. This exceeds the minimum width of a 4-foot bike lane with a 1.5-foot curb and gutter according to the Federal Highway Administration. This 5-foot width will maximize safety and comfort for both vehicles and bicyclists. Sidewalks will parallel all roadways and bike paths with a minimum width of 10 feet and will be constructed according to ADA standards. There will be signalized pedestrian crosswalks at each leg of the intersection. And to accommodate for the expansion of South Shaw Lane, a pedestrian refuge on South Shaw Lane between Anthony Hall and the Engineering Building will allow for safe crossing by pedestrians of all 5 lanes. A new parking lot 79EB, north of the new academic building, has a capacity of 25 spaces. The parking spaces are 9 feet wide and 18 feet long with an aisle width of 24 feet to match the dimensions of parking lot 79EA. This smaller lot could be used solely for faculty and staff. The existing parking lot 79EA, has an original capacity of 79 spaces, but it was altered to 78 spaces to include a handicap spot. This makes the total parking capacity 103 spaces. A new parking lot 79EB, north of the new academic building, has a capacity of 25 spaces. The parking spaces are 9 feet wide and 18 feet long with an aisle width of 24 feet to match the dimensions of parking lot 79EA. This smaller lot could be used solely for faculty and staff. The existing parking lot 79EA, has an original capacity of 79 spaces, but it was altered to 78 spaces to include a handicap spot. This makes the total parking capacity 103 spaces. Parking lot 40 and lot 39 will be removed for the expansion of South Shaw Lane. The removal of these two lots will remove 549 total parking spaces. To make up for this capacity loss, a multi-level parking structure is proposed to be built in the footprint of lot 40. Using ramp 1 for reference, which is located on South Shaw Lane east of the CATA station, the parking capacity would be 1,094 total spaces. The closure of North Shaw Lane to vehicle traffic eliminates the main entrance and exit for lot 50 and lot 38. A new roadway connecting lots 50 and 38 to the expanded South Shaw Lane, as well as connecting to the new parking structure, is proposed to be constructed. This new roadway would have similar lane width to Shaw Lane of 11 feet. The current parking capacity of the parking lots in the immediate vicinity of the project site is 787 spaces. With the adjustments detailed in this design, the future parking capacity would be 1,351 spaces. This is an increase of 564 parking spaces that could be used by students, commuters, faculty, and visitors. The proximity to Spartan Stadium would create a revenue source for paid parking on game days beyond the normal parking revenue. The total time it will take to establish this design is roughly 122 days. This includes the removal and installation of the material listed. The cost for the transportation engineering specific features is roughly $1,021,553. It is important to note that this time frame and cost does not include the parking garage structure. Further knowledge and expertise would be needed to establish a cost estimate and construction schedule. From the research I gathered, the price of a multi-level parking structure can vary anywhere from $200,000 to $10 million. Using RS Means data, a conservative cost estimate of $8.7 million was referenced.
Hello, I am Hannah Watts and I am the hydrology engineer at Superior Spartan Engineering, and I have completed the hydrology design for the Shaw Lane Power Plant Rehabilitation Project. The design objectives for this hydrology portion of the project are to create a comprehensive hydrological system that can properly maintain the safety of the surrounding land and community. In recent years, the Red Cedar River has seen excessive flooding onto Michigan State's campus, blocking off roads, sidewalks, and getting very close to buildings that are located next to the river. The emphasis of my hydrological design was to minimize the amount of stormwater that is contributing to the river in order to reduce the amount of potential flooding during storm events. The main element of this idea is that the post-development outflow from the stormwater sewer system does not exceed the pre-development outflow. The majority of the surrounding stormwater sewer systems drain directly into the river without any sort of detention facility to control the outflow to maintain natural conditions. The Ingham County Drain Commissioner regulates that the outflow from a stormwater detention system needs to be limited to 0.15 cubic feet per second per acre of land drained. The last element of the hydrology design is to create a stormwater system designed to handle a runoff capacity created by a 10-year storm, also as specified by the Ingham County Drain Commissioner. The emphasis of my design for the project area was to implement many different low-impact development features in order to reduce the overall amount of runoff throughout the project area. I also emphasized evaluating the existing stormwater sewer systems within the project area rather than excavate all of the existing systems and create a new one. I believe this can properly handle the capacity of stormwater generated while also being a more cost-effective plan. The entire project area is shown in the lower portion of this figure, yet it also shows the northern area where one of the 2 retention ponds will be constructed. Overall, there are 5 pipe networks involved in the project area, 32 existing pipe sections to be replaced, 20 catchment areas, 2 retention ponds, 20 rain gardens, an addition to the parking lot, and a green roof implemented on top of the new structure. The specific discussion of all these elements and the plans are included in this presentation. The main low-impact development features implemented in my design are a green roof, rain gardens of various sizes located around the project area, a pervious pavement design for the parking lot, including the addition to the parking lot, and 2 retention ponds. This slide shows a map of the majority of the building site with many of the low-impact development features labeled, as well as the location of the new structure and parking lot addition. The green roof is located on the roof of the new structure. The gutter system surrounds the roof and will use gravity flow to drain the stormwater to the north end of the building. The green roof will drain down into the stormwater sewer below and contribute to the flow in Pipe Network 5. This is the pipe network that is drained into Retention Pond 2. The existing parking lot, with the addition to the parking lot, will be paved with concrete unit paver blocks, with a gravel substance to fill the gaps. This method of paving increases the amount of infiltration of surface runoff into the ground below. This reduction of runoff decreases the amount of water contributing to the stormwater sewer in this area. This is a crucial element to the design. With the building of a new structure and the addition to the parking lot, a large amount of new impervious area will be created and will increase surface runoff. Any design elements that reduce runoff are beneficial to the project area in terms of limiting the increase in runoff during storm events. This is somewhat more expensive than a typical paving process. The blocks will be laid down with gravel added in between the blocks. There are a few maintenance costs associated with this plan, other than adding additional gravel if there is natural depletion or displacement of gravel. If there is a crack in one of the blocks, for example, a new block can easily be added rather than replacing an entire portion of a regular asphalt parking lot or placing a patch. I believe the hydrological benefits of this pavement design outweighs the additional cost. Implementing retention ponds rather than detention ponds was decided because they are more environmentally friendly than detention ponds, and they will not contribute stormwater to the Red Cedar River. There are 2 retention ponds for the project area. Pipe Network 3 will contribute to Retention Pond 1 through the addition of the new construction of Retention Pond 1 stormwater system. Pipe Network 5 will contribute to Retention Pond 2 through the addition of Retention Pond 2 stormwater sewer system. The stormwater sewer system emphasizes replacing the existing pipes that are not to code. This code is specified by the Ingham County Drain Commissioner, stating that the velocity within the pipe must be between 3 feet per second and 10 feet per second. The process of calculating the correct pipe diameter for each pipe section started with dividing the total project area into catchment areas, separated by each stormwater sewer node. There are 5 pipe networks associated in the project area, and those all have different peak flow rates calculated based on the catchment areas that are drained and the pipe networks within them. In each network, the diameter was calculated for each pipe section using Manning's equation. The velocity of the water in the pipes is calculated using the calculated flow rates and diameters. If the velocity is between the 3 feet per second and 10 feet per second, then the diameter is recorded as the recommended diameter sized to the nearest commercially available diameter pipe. The AutoCAD file has many of the pipe sections labeled with the diameter and material of the existing pipe. If the existing pipe section is a diameter that maintains a proper velocity when calculated, then that pipe section will remain intact. If the pipe section is labeled at a diameter that creates a velocity that is not to code, or if the section is not labeled, a recommended diameter is provided and the pipe section will assume to be replaced. The 20 catchment areas and the general flow directions are shown in this figure on this slide. The 5 pipe networks are specified in this figure. Pipe networks 1 and 4 drain to existing stormwater sewer main systems that flow south of campus. Pipe network 2 drains north to an existing network. Pipe network 3 drains to retention pond 1, and network 5 drains to retention pond 2. A total of 32 pipe sections were calculated to be replaced, by either having an incorrect diameter or a diameter that was not labeled. All of the pipe sections that are going to be replaced are labeled with a red pipe and red label specifying the section name. These figures are also shown on the following slide. Detention ponds are required to be calculated to hold a capacity of a 100-year, 24-hour storm event specified by the Ingham County Drain Commissioner. With the selection of retention ponds rather than detention ponds, the ponds were calculated to hold 2 consecutive 100-year, 24-hour storms as a form of contingency. Retention Pond 1 sewer system is made up of 6 18-inch diameter pipe sections to bring the water from Network 3 to Retention Pond 1 using gravity flow. Retention Pond 2 sewer system is made up of 6 12-inch pipe sections to bring the water from Network 5 and the green roof to Retention Pond 2. Retention Pond 1 has a total volume of 92,951 cubic feet and is located at a low topographical area north of the project area. Retention Pond 2 is located just south of the new structure with a total volume of 26,939 cubic feet. It is important to make sure that these are part of the attractive landscape surrounding the pond, rather than just being an eyesore. This can be done by planting trees and shrubbery around the ponds or even adding a fountain feature. The total cost of the hydrology portion of this project is estimated to be $1.1 million. The main components of this cost are the pipes to be replaced and added to the retention pond sewer systems. There are a total of 18 12-inch diameter pipe sections with a total length of 216 feet, and a total of 26 18-inch diameter pipe sections with a total length of 268 feet. There are 20 rain gardens, the green roof, the repaving of the parking lot, 2 large retention ponds to be excavated, and the engineering fee. The total estimated construction time for this project for the hydrological items is 71 days. The hydrology design is involved with many other elements of this construction due to it involving large portions of the project area. The structural engineer and I coordinated the construction of the green roof with my design and his calculation of the load caused by the new roof. The transportation engineer and I coordinated the addition to the parking lot when he provided me with the proper location and size of the addition. The pavement engineer and I coordinated the repaving of the parking lot, including the addition, with the unit pavers rather than the typical pavement.
Hello, ladies and gentlemen. My name is Ben Gurton, and I am the structural engineer for our team. The structural engineering design objectives were to design a structural framework for the new STEM building that will satisfy load resistance, factor design, and serviceability requirements, and to design an architectural layout that meets the university's needs that abide by International Building Code specifications. For structural and architectural design organization, the building was separated as 2 individual sections. Section A is 160 feet in length and 80 feet in width. Section B is 200 feet in length and 80 feet in width, and the connector hallway between them is 20 feet by 20 feet. The university requested the basement level be used for storage and utilities, the first floor to be used for dean's offices and computer labs, the second and third floors to be used for classroom spaces, and the fourth floor to be used as a space for faculty offices, a department office, and laboratories. The design solution features are displayed on the column to the right, and on the next two slides, the amount of square footage for each room type is displayed. Total space used for educational purposes totaled 53,936 square feet. Per Section 1004.5 of the International Building Code, the footage required per person is 20 square feet in an educational setting. Therefore, the maximum capacity is 2,696 persons. Each floor has 5 staircases and 5 elevators. Per Section 1006.3.2 of IBC, the minimum number of accesses for a building that has an occupant load between 501 per 1,000 people per story is 3. The next few slides display architectural layout drawings for reference. The red squares denote the location of a structural column. The structural design of the new STEM building is a steel frame design using grade 50 A992 steel. Each floor and the roof is comprised of a 6-inch concrete slab with rebar reinforcement. The total elevation of the building above surface level is 56 feet, and each floor, including the basement floor, is 14 feet in height. Note that the design of the concrete slab, the design of steel connections, and the design of the foundation was out of the team's scope of work. This was subcontracted out to a different company. The dead load is comprised of 75 pounds per square foot from the weight of the concrete slab and an additional 20 pounds per square foot from the weight of the interior building objects such as furniture, walls, and ceiling materials. The live load is 75 pounds per square foot. This was an assumption given to us by our structural professor, Dr. Kador. The roof live load is 20 pounds per square foot per Chapter 4 of ASCE 7 based on the design of flat roofs. The snow load is 20.79 pounds per square foot per ASCE 7 equation 7.3-1 and based on the location of the building being in East Lansing, Michigan. I was directed to use a wind load of 10 pounds per square foot as an assumption, and the exterior wall, which is comprised of lightweight concrete masonry units, has a uniformly distributed load of 441 pounds per foot. A preliminary design was modeled in SAP 2000, which is a structural analysis modeling software. The following load combinations that were simulated in the program are disclosed in the table on the left. The governing load combinations that generated the design forces are shown on the right. The design forces are tabulated on the next slide. Tabulated here is our design solutions for steel members. The specific columns were selected because they all withstand the factored compressive forces as shown in the table below. All of these columns are non-compact sections, therefore local buckling does not occur. The table displaying slenderness and local buckling limit state information is included in the next slide. As you can see in the table, the shear and moment strengths of the beam selected are greater than the observed design forces. In this table, the slenderness ratios are shown to be less than the limit state values, making both beams classified as compact. Therefore, local buckling does not occur. Lateral torsional buckling does not occur because the beams are braced continuously by the concrete slabs that they are supporting. The maximum allowable live load deflection according to section 1604.3 of IBC is 1 inch. The deflection from the live load for both beams meets this requirement. All bracing members' compressive and tensional strengths are greater than the observed factored forces observed from the SAP 2000 computer model. All braces are classified as non-slender, as the slenderness ratios are less than the limit state. Therefore, local buckling does not occur. In the next few slides, structural elevation drawings are provided. The unit prices for construction materials were $145 per cubic yard of concrete, $950 per ton of rebar, $4 per pound of grade 50 steel. According to the RS Means catalog, the unit price of exterior windows was $2.43 per square foot and $5.92 per square foot of exterior wall. The design fee for our company was $40 per hour, and our engineering fee was 2% of the entire structural cost. Shown in this table is the cost for every structural construction material. The overall cost of the structural materials is a little over $8.1 million. The cost of concrete includes a 20% add-on expense for potential loss of concrete and a 20% construction cost. The cost of steel includes a 10% add-on to pay for connections and a 20% add-on for fabrication and erection. Itemized cost tables for steel and concrete are shown in the next slide. By utilizing the RS Means catalog, the estimated prices for plumbing, HVAC, and electrical systems were computed. This brings the price of the total building to nearly $12.3 million. Shown in the table are the construction times for each section of the new building. It takes 30 days for the concrete to cure and 20 days to install the steel materials on each level. The total construction time for structural engineering is 354 days, which is just under a year. Structural engineering cooperated with hydrology in the design of green roofs with respect to the amount of loading the green roof would have on the building. Now I would like to say thank you to the judges panel for your attention to the structural engineering portion of this design project.
Hello, my name is Jillian Pelzer, and I am the Superior Spartan Engineering Pavement Engineer for the Shaw Lane project. The object of this project is to provide Michigan State University with an engineering design for infrastructure improvements that will positively impact the campus and nearby community. Specifically, the goals of this project relating to the pavement's design aspects consist of improving Shaw Lane Road, Red Cedar Road, increasing the amount of parking spaces through the improvement of existing and creation of new parking lot pavements, and including environmentally focused elements. In order to begin this process, the surveil of the current condition of the pavement on these roads has been taken into account. As shown by the figures, Shaw Lane Road consists of severe amounts of distress. The most prominent distresses are structural distress in the form of longitudinal cracking and environmental distress in the form of thermal cracking. There is also some structural distress consistent with fatigue cracking in some areas of Shaw Lane Road, and several potholes are present, such as in Figure 2. Red Cedar Road has also small amounts of environmental distress in the form of thermal cracking and minimal longitudinal cracking. After the observation of the pavement condition present, in order to begin our design process, initial data was collected. This initial data consists of the average annual daily traffic, or AADT, values provided by the Superior Spartan Engineering Transportation Engineer. Once the AADT values were determined, the truck factor for rigid and flexible pavements, estimated growth rate, lane distribution, directional distribution, and percentage of trucks were used to calculate the equivalent single axle load, or ESAL, values for each roadway, as well as the ESAL 20-year values for rigid and flexible pavements. Climatic data was also determined through the use of the LTPP Bind online tool, which resulted in a maximum air temperature of 52 degrees Celsius and a minimum air temperature of negative 28 degrees Celsius, or PG 52-28. Through the use of Ingham County soil data, the resilient modulus, or MR, value for the area was determined to be 3,500 psi due to the sandy clay soil present. For the Shaw Lane project, 4 design alternatives were created consisting of a mill and fill design for Alternative 1, an overlay design for Alternative 2, a new rigid design for Alternative 3, and a new flexible design for Alternative 4. The cost per lane mile for each of these alternative designs was determined by first calculating the layer thicknesses for each design using the PaveExpress software. The software incorporated the ESAL and MR values previously determined. For the Alternative 1, or the mill and fill design, the layers consisted of an aggregate base, subbase, and a hot mix asphalt, or HMA, overlay after the removal through milling of a dense graded asphalt layer. Alternative 2, or the overlay design, consists of an aggregate base, subbase, asphalt layer, and an HMA overlay. However, this design simply places the HMA overlay over the unaltered asphalt layer. Alternative 3, or the new ridge design, consists of the aggregate base and PCC layer. Alternative 4, or the new flexible design, consists of an aggregate base and aggregate subbase layers. Once the layer thicknesses were determined to find the cost per lane mile, the thicknesses of the altered or redone layers, the lane width of 11 inches, and the value of 1 mile were multiplied to determine the area and volume. The unit of this area or volume was then converted appropriately to be multiplied by the price of the layers material provided by MDOT. The cost per mile was determined by multiplying the cost per lane mile by the number of lanes, in this case 5. The future estimated maintenance costs were determined through combining the maintenance cost and the use cost determined from the LCCA. In order to implement the life cycle cost analysis, the LCCA Excel calculator and the LCCA maintenance strategies article, both provided by MDOT, were utilized. This allowed for the initial rehabilitation, maintenance cost, traffic control, and use cost to be determined. These variables were inputted to conclude the present worth, or PW, and the equivalent uniform annual cost, or EUAC, values. The present design of Red Cedar Road currently consists of 3 existing lanes north of the intersection and 4 existing lanes south of the intersection that will be expanded to 5 lanes for the entire roadway. South Shaw Lane Road currently has 2 existing lanes that will be also expanded to 5 lanes. In order to do this, the new flexible design was chosen to create the new lanes, and a mill and fill design was chosen for the existing lanes. The mill and fill design for Red Cedar Road and Shaw Lane Road differ, however, due to large amounts of distress on South Shaw Lane Road. For Shaw Lane, the entire 5 inches of the asphalt layer was removed and redone with an HMA overlay, as opposed to only 2 inches of pavement being milled and replaced with an HMA overlay for Red Cedar Road. This was done in order to increase the longevity of the existing lanes for its mandatory 20 years of service life, but also to be more cost-effective than removing the existing layers entirely and using a new flexible pavement to remake them. Thus, to determine the construction cost, the cost per lane mile for the new flexible design was multiplied by the new number of lanes, and the cost per lane mile for the mill and fill design was multiplied by the number of existing lanes for Red Cedar Road and South Shaw Lane Road, respectively. Then these costs were multiplied by the amount of road being worked on, which was approximately 0.3 miles for South Shaw Lane Road and 0.2 miles for Red Cedar Road. MDOT also provided the information for the construction time estimate, which consisted of the amount of a specific material that can be added or removed in one day, and then by multiplying this value by the overall amount of the specific material, the number of days per task were determined. This same process was taken into account to determine the removal cost of North Shaw Lane Road and the creation of a 2-lane bike path, as well as the amount of time for these endeavors to be completed. A new roadway was also completed in order to enter the proposed lot number 40 parking structure. The new roadway is a 2-lane road with 1 lane in the northbound and 1 lane in the southbound directions. Alternative 4, or the new flexible design, will be used to create this roadway, and the cost estimate and construction time for this roadway is determined using the same processes as previously stated. This is a visual representation of what the pavement design in terms of number of lanes and their directions will be for Shaw Lane Road, Red Cedar Road, the new roadway, and the bike path. The proposed parking structure is also incorporated into this design. However, further analysis of the structure is necessary in order to determine its pavement design, construction cost, and construction time. The amount of parking spaces in this parking structure is estimated to be 1,094 spaces. In regard to parking lots, lot number 39 will be removed and replaced with green space, and the STEM building parking lot will be a new flexible design created with a clay pavers brick top layer. This is an environmentally friendly, durable, and low-maintenance alternative to traditional HMA material. More details on its design and benefit are provided by the Superior Spartan Engineering hydrology engineer. The cost estimates and construction times for these developments are provided as well. The total construction cost and total construction time were calculated by combining all of the individual cost estimates and combining all of the construction times respectively. The parking capacity is expected to increase from 787 parking spaces to 1,351 spaces. In terms of sustainability, a certain percentage of reclaimed asphalt pavement or global modified pavement is recommended to be incorporated into these designs due to recycled materials being green and cost effective. A look into the process of creating wrap pavement is shown in the figure below. The inclusion of rain gardens and a green space into the parking lot designs has also been incorporated, which increases the sustainability of the Shaw Lane project. These environmentally friendly features, as well as the improvement of Shaw Lane Road, the improvement of Red Cedar Road, the improvement and creation of the parking lots, have resulted in the completion of the goals of this project. Thank you so much for your time. Have a great day.
The following permits were needed in order to construct the new building. The State of Michigan building permit from the Department of Licensing and Regulatory Affairs was needed to build a structure in East Lansing, Michigan. A tap-in permit was needed to tie into existing infrastructure. An occupancy permit was needed for the building to be open to students and faculty. An elevator permit was needed for elevators to operate. A soil erosion permit was needed for disturbing the surrounding soil. The U.S. EPA permit was needed to discharge pollutants into the Red Cedar River. The right-of-way permit was needed to work in the right-of-way. A paving permit was needed to pave. The ICDC crossing permit was needed for drainage crossings. A tree removal permit was also needed to remove trees. Lastly, a parking permit was needed for the construction crew to park. The construction crew is to start on January 1st, 2021. The structural part of the project will take approximately 354 days and end on November 24th, 2021. Shaw Lane Road, Red Cedar Road, and the surrounding parking lots will take about 41 days to be paved, and construction will end on April 15th, 2022. The hydrology portion will start after the paving. This will take about 71 days, which will end on June 25th, 2022. The transportation construction will start after the hydrology construction, taking about 122 days, which will end on October 23rd, 2022. A contingency of 2 weeks was added into the construction schedule to accommodate for unforeseen circumstances. The project is scheduled to be completed on November 6, 2022. The structural cost estimate is about $12.3 million. The total pavement estimate is just short of $800,000. The hydrology cost estimate is about $1.1 million. And lastly, the transportation cost estimate is about $9.7 million. With a contingency factor of 15%, the total cost of the Shaw Lane Rehabilitation Project is estimated to be about $27.5 million. This cost does not include labor. This concludes our presentation. If you have any questions, feel free to reach out to us. Our emails are listed below. Thank you.